lecture number 2 of the electrical drive. This lecture we are starting with the fundamental torque equation of the drive. That is the fundamental torque equation. The drive is depending upon the two types of torques. One is the motor torque, another is the load torque. The relationship between the motor torque and load torque is like that. If I draw the motor load combination, this is the motor, which is driving a mechanical load. Now, in case of motoring action for the motor, this is the direction of motor torque, in which direction motor is also rotating, that is omega m. And the load torque is acting on the opposite side of the motor torque. It is continuously opposes the motor torque. This is the direction of the load torque, from which we can derive the equation of the motor load torque. Equation becomes motor torque minus load torque will be the ddt of j omega m, where j is the moment of inertia of the motor load system. Okay. Now, if I derivative this becomes j d omega m dt plus omega m dj dt. Okay. Then for the drive, with constant inertia, obviously ddt of the j or inertia becomes 0. Now, the fundamental torque equation of the motor load system becomes Tm minus TL equals to j d omega m dt. This is a fundamental torque equation of the motor load system. Okay. Now, from which this d omega m dt, j d omega dt stands for the acceleration of the motor load system. Now, from this equation we can derive three criteria. Number 1, A, if the motor torque is greater than the load torque, then j d omega m dt is positive. Okay. This stands for motor accelerates. Okay. Acceleration of the motor load system. Now B, if motor torque equals to load torque, then J d omega m dt equals to 0. That is, motor and load are in steady state condition. No acceleration, no deceleration. No acceleration or deceleration. Now number C, if the motor torque is the less than load torque, that is J d omega m dt is negative. This stands for motor decelerates. Deceleration. Okay, these are the three basic criteria of the motor load system or motor relationship between the motor torque and the load torque. Okay. Now the energy associated with the dynamic torque equation, that is the energy associated with J d omega dt will be stored in the motor load system, will be stored in the motor load system in terms of the kinetic energy, that is half J omega m square. Okay. Now this all about the fundamental torque equation of the motor and load. Now coming to the quadrant operation of the motor load system or the electrical drive. Quadrant operation of electrical drive. Now we are having 4 quadrants. This is the omega axis, this is the torque axis. Okay. Based on which this is the first quadrant, second quadrant, third quadrant and fourth quadrant. Based on which the motor load system will act as the motoring action or the braking action, it depends. Okay. Now I am going one by one. Say I am drawing the same diagram. This is the axis of the plus omega m. This is minus omega m. This is positive torque. This is negative torque. Okay. Now say there is a pulley of the motor. This is the hoist operation where it is acting to uplift of a loaded cage. The cage is loaded. Okay. And in this side there is a counterweight is present. This is counterweight. Okay. And the motion is the upward. This is loaded cage. Then this motion is taking as the positive. Okay. This is plus omega n. Then obviously the torque, motor torque, will be acting in this direction Tm, and the load torque is opposing the motor torque TL. Okay, this is the situation in the first quadrant, and we are applying. This is the load torque for the first quadrant. This is the load torque we have applied. Okay. Now in the second quadrant, when we drive the same cage but no load, the cage is not loaded, that is the empty cage. Obviously at that moment counterweight becomes heavier than the cage. Okay, this is the counterweight. But the cage is empty. No load is associated with the cage. But motor direction is still in the same direction, omega. This is plus omega m. Okay. But load torque is in this direction. This is the direction of the load torque, and motor torque will be opposite to the load torque. Then obviously the torque in the first quadrant we have applied will be the greater than, or the torque is applied to the motor in the second quadrant, obviously less than the first quadrant. Okay. Say this amount of torque is applied because the cage is empty. This is the counterweight, and this is empty cage. Okay. Now in the third quadrant, if the motor is in the second quadrant, motor is acting to upliftment of the empty cage, but in this third quadrant, this torque becomes the negative with respect to the positive quadrant. Okay. Now in the third quadrant, motor is lowering the empty cage. The action is downward. Is the counterweight. Okay. Then this is the direction of the speed, and torque is negative, means as previous the load torque is acting in this direction, but motor torque is acting in this direction. Okay. All the sign before the torque and the speed with respect to the first quadrant operation. Okay. First quadrant is the taking as a standard reference. Now in the fourth quadrant, when the motor is lowering the loaded cage, then obviously the loaded cage is heavier than the counterweight, and for this the load is basically driving the motor. Okay. When lowering the loaded cage, the direction of omega is in this direction, minus omega m. Now torque is positive here, that is this is the direction of the motor torque, and this is the direction of the load torque. Okay. Now this is the first quadrant operation, quadrant 1, quadrant 2, quadrant 3, quadrant 4. Okay. Now this LC means loaded cage, EC means empty cage. Okay. Now it is clear that in quadrant 1, I am go back to the previous page. For the quadrant 1, omega is positive, motor torque, motor speed, omega m, motor torque is also positive, then power, motor power is also positive. Okay. That is, this means this is called forward motoring. forward motoring operation. Okay. Now quadrant 2. Where omega m is positive, but torque becomes negative, hence the motor power becomes negative. That is, instead of the taking or consuming power from the power source, the motoring is delivering. Still, the motor is rotating in the same direction, but it delivers the power. That is called forward braking. Now quadrant 3. Where omega m is negative. Now this is the reverse motoring operation. Okay. Motor torque is also negative, becomes power positive. P equals to omega into T. This is called reverse motoring. This is called reverse motoring. And finally, quadrant 4. Omega m negative, torque positive, power becomes again negative. This is called reverse braking. Okay. That is, when braking mode of operation, instead of consuming the power from the power source, the motor is delivering power to the source. Okay. But motor is running in the same direction. Now coming to the next one is the calculation of inertia. That is equivalent values of drive parameters. Now we have the load, different kind of loads are there. Basically, we are considering two kind of loads. One is the rotational load, another is the linear motion load. Okay. Now first one, loads with rotational motion. Now if I draw the diagram, say this is the motor, and after that the motor is coupled with, directly coupled with a load having load torque TL0. Now obviously if this is the direction of the motor speed, then load torque will be acting opposite to the motor speed. This will be the direction of the motor torque, load torque. This will be the direction of the load torque. Okay. Now after that, another load is connected with a gear arrangement. This is the gear arrangement. Another load is connected, load of TL1. Now if the load torque 0 is, the speed is in this direction, the shaft is rotating in this direction, omega is rotating in this direction. Then the speed is, say, this is omega m, omega m1. Then the load torque will be acting the opposite to the speed in this direction, correct? This is the clockwise, this is also clockwise, this becomes anti-clockwise. Okay. Now say we are considering this inertia is J0 and inertia of this load is, say, J1. Okay. And the gear ratio, say this is N, this is N1. These are the gear teeths. Then obviously the speed of the machines depending upon the speed of the loads is inversely proportional to the gear teeth ratio, that is omega m1 by omega m, we can write that is n by n1, which can be written as a1. Say this is a1. Now the kinetic energy due to the equivalent inertia, the kinetic energy due to inertia, or rather due to equivalent inertia, better to say due to equivalent inertia, because we have to calculate what is the equivalent inertia. Due to equivalent inertia must be same must be same as the kinetic energy must be same at kinetic energy of various moving parts of the motor load system. Or motor load arrangement, whatever it may be. Okay. Now we can write then half of the kinetic energy is the half of J is the equivalent moment of inertia of the entire system. Okay. J omega m square can be equated as half of J0 omega m square, because this J is faced by this motor. Okay. And the motor speed becomes is the omega m is that half J0 omega m square plus half J1 omega m1 square. Okay. Now dividing the both side by the omega m, that is J will be equals to J0 plus J1 omega m1 by omega m square. Okay, that is J equals to J0 plus J1 a1 square. Okay, this is the equivalent inertia referred to the motor shaft. This is the equivalent inertia referred to motor shaft. Okay. Now next is the power. Same thing, power at the loads and the motor. Power at the loads and the motor must be equal must be equal. Okay, and if I consider must be equal if the gear transmission efficiency is considered as transmission efficiency is considered as eta eta 1, then we can write what we can write, the equivalent load torque referred to the motor shaft, motor is running at the speed omega m, will be TL0 omega m plus TL1 omega m1 whole divided by eta 1. Okay. Now if I divide both the sides with the same thing omega m, that is the equivalent load torque becomes TL0 plus TL1 by eta 1 omega m1 by omega m, that is TL equals to TL0 plus TL1 by eta 1 into A1. Okay, this is the equivalent torque referred to motor shaft. Okay. Now, from these above two equations, if there are number of loads are connected through the gear arrangement, then we can write for m number of loads. For m number of loads connected with the gear arrangements, then we can write from these above two equations J equals to J0 plus J1 A1 square. Okay. Equivalent inertia will be J equals to J0 plus J1 A1 square plus J2 A2 square plus Jm Am square. Okay, and the equivalent torque referred to the motor shaft becomes TL0 plus TL1 by eta 1 A1 plus TL2 eta 2 A2 plus TLM eta m Am. Okay. This is all about the equivalent inertia of the rotating type of loads. Okay, in the next lecture, we will discuss about the loads with the linear motion. Okay, thank you.